We are recording. All right. If everybody looks at the classwork opening exercises for this packet, it gives us a thought experiment. It says, suppose a ball is dropped from initial height h sub 0. Now, what do you think this little 0 here is supposed to signify? What do you think that little 0 is right there? Right, so if I'm dropping from h sub 0, how many times has that thing bounced thus far in our experiment? 0 times, right? And then, each time it rebounds, its new height is 60% of its previous height. Okay? So, now it asks, what are the first 4 rebound heights? H1, H2, H3, and H4. What do you think the 1, 2, 3, and 4 mean? How many times it bounced? So, I drop the ball from H0. It bounces once and rebounds up to H1, right? Then it bounces another time and rebounds up to, well, here, H2. Bounces again, rebounds up to H3, bounces up one more time to H4. Okay? And then after that, the problem really don't care, does it? But what are the first 4 rebound heights after being dropped from a height of H0 equals 10 feet? What does that mean in English? When it says after being dropped from a height of H sub 0 equals 10 feet, what does that mean in English?
It's being dropped from 10 feet up.
It means I'm being dropped from 10 feet up. Okay? So now that we got all that figured out, we've unpacked the problem. What is the first height that this ball rebounds to after bouncing? How high does it bounce? What do you think, Jeff? If it rebounds to 60% of its previous height, right? This is an important little clause in this problem, don't you think? Who got that? Where do you come up with that, Caden?
Well, if you think of like 60%, 10, which is like
6 feet.
Yeah.
So think about this. How do you do 60% as a decimal?
0.6.
0.6, right? Move the decimal place 2 times to the left, right? So 60% is 0.6, right, Cam? Now, 0.6 times 10, now we're moving it 1 time to the right again, is 6 feet. So H sub 1 equaled 10 feet times 0.6, which equals 6 feet. What does H sub 2 equal? Somebody other than Caden.
It would be 6 times 0.6.
It would be 6 times, so H2 equals 6 feet times 0.6. And if I do that, 3.6 feet, that's what I get. Now, 60%, right. Every time it bounces, it only comes back to 60% of what it was at the previous time. So what is H sub 3? How do I find H sub 3? What do you think, Trey? How do I find H sub 3? Because I know you've been listening this whole time. What do you think, Tyler? See, I know the two of you guys can get this, but I need you in touch with me, okay? Need you engaged. How do I get H sub 3? Go ahead, Miss Millis.
Take the answer of H sub 2 and then times it by 0.6.
So my answer for H sub 2 is 3.6 feet, and I times it by 0.6 again. And I get what? what is that, 2.16?
I did that on the calculator.
2.16 feet. Good. And very good. H sub 4 now.
1.296.
How'd you get it?
H sub 3 times 0.6.
H sub 4 equals H sub 3, which was 2.16 feet, times 0.6, which equals, and what was that number again?
1.296.
Chickens?
Feet.
No,
Feet. 1.296 feet. Okay. Now, Eureka wants to throw a curveball at you. Suppose your initial height is A feet, Jesse. A. Not A, but A, the letter A, number of feet. Can I figure out an expression for the first 4 rebound heights? If I'm dropping it from a number of feet, how high does a rebound after the first bounce? What do you think, Jasmine? You got an expression for that? I'm sorry? H sub 1 is the variable, but what's an expression for H sub 1? So H sub 1 equals what? Got help? You got some help, Liv?
I think I do.
All right.
H sub 1 equals A times 0.6.
Or we like to put our numbers before our variables, right? 0.6 A. And rebound 2 then. If rebound 1 is 0.6 A, what is rebound 2? So I took 60% of A and got 0.6 A. And now to get the second one,
3.6. Or no.
close. What's 0.6 times 0.6?
36.
Where's the decimal point?
0.36.
0.36. I couldn't hear you. Okay. Now, third bounce. Where do you think it bounces up to, Caleb?
This is just the same thing as up there.
0.36 times 0.6, right? Won't it just be this with the decimal place moved over 1 to the left? So it's 0.216 A. And lastly, number 4 would be 0.1296 A. Now, I'm going to add a little wrinkle to this, because this is 0.6 A. Is there a shortcut? And not even a shortcut. Not even what's that, Kaya?
0.6A squared.
Not 0.6A squared, but 0.6. I'm squaring the 0.6, right? Times A. What about the third one? 0.6 cubed times A. And then the last one, 0.6 to the 4th power times A. Now, riddle me this, Batman. The stuff in the height column that we got here and the stuff in the column that I made up, those mean the exact same thing, don't they? I've just written it differently to illustrate the relationship between the 60% and the height. Does that make sense? And then this really answers letter C. How does each term relate to the term that came before it? I take the previous term and multiply by what? 0.6. I take the previous term and multiply, that's an asterisk, by 0.6. Now, last question on the first page. Suppose the initial height is 8 feet, and each rebound, rather than being 60% of the previous height, is r times the previous height, where r is between 0 and 1. It is confusing, but what did we just do? I replaced 0.6 with what? I replaced 0.6 with r. So, A1 is going to equal what? It's going to equal A times what? R. A2 is going to equal AR squared. Do we see where this is going? A3 AR cubed. A4 is AR to the fourth. How about A sub n? It's asking, what is the nth bounce? Now I'm just replacing this number here with a variable and calling it n, right? So what is the nth bounce? Well, A sub n equals A times R to what power? The n power. Easy peasy lemon squeezy, right? Now we get into definitions. It's asking, what kind of sequence is the sequence of rebound heights? It's asking what kind of sequence. Who remembers the type of sequences that we went over in Algebra 1? So we haven't done this in a couple of years. Who remembers the type of sequences we learned about in Algebra 1? There were two of them. I remember, Kaya, because we were in class together when we learned them. There was the arithmetic sequence. Who remembers arithmetic sequences? Put your phones down, please. Who remembers arithmetic sequences? I got one person. Who remembers geometric sequences? Arithmetic sequences are sequences where I add or subtract the same number every time. And actually, I always say add because in order to subtract, I would just add a negative number, right? A geometric sequence is when I multiply by the same number every time. What number was I multiplying by every time in the first example? 0.6, right? What about the second example? What was I multiplying by every time? R, right. Just because it's not a number doesn't matter. We were still multiplying by R, right? Okay, so this was called a geometric sequence. Now, it's a geometric sequence, but there are two types of geometric sequences. This one is called geometric decay. Why do you think it's called geometric decay? Because it's going down, right? It's going down. Okay? There's another name for it. We call it exponential decay. Okay? Why do we have two names for it? Well, let me ask you, what color shirt are you wearing, Kaya? Blue? What about you, Riley? What color sweater are you wearing? They're not the same color. So could we call your shirt, Kaya, could we call it, I don't know, lapis? Lapis is a kind of blue, right? or sky blue or azure. Those are all kinds of blues, right? Or cyan.
Oh, isn't that red?
No, cyan's blue. Cyan's blue. Lapis? Lapis.
Cyan is more of a teal.
You see my point though, right?
But it's not different colors, it's different shades.
But
But I do
there's a subtle difference between these terms. You don't need to know the difference between you don't need to know the reason for the difference between these terms right now. They are similar enough for you at this point in your life where these mean the same thing. Okay? So somebody's going to say geometric, and another person's going to say exponential, and because you guys care about math so much, you're going to get into an argument about it, right? Yes. And you're both right. So they're going to argue about which one's blue. Well, they're both blue, right? Mr. Mullenberg, how you doing?
Yeah. I'll come back later.
All right. Suppose, now we're off to letter F. Suppose that we define a function f with the domain of the positive integers so that f1, or f of 1, equals the rebound height. f2 is the second rebound height, and continuing so that f sub k is the kth rebounding height for the positive integers k. What type of function would you expect f to be? What kind of function would you expect f to be? Exponential decay, right? We're going to graph it. We're going to say a sub 0 equals 10. And we're going to let r equal 0.6 again. We already know what the first four terms of that are, right? Actually, the first five if I count a sub 0, right? A sub 0 is what? 10, right. So I put a dot right there. And if a sub 0 is 10, a sub 1 equals 60% of that, so a sub 1 equals 6, 3.6, 2.16, 1.2, what was the other one? 1.296. So that's 1.296, so about 1.3. How about f or a sub 5? The easy thing is I just take a sub 4 and do what to it? Yeah, so can somebody do that on their number machine?
What was it?
1.296 times 0.6.
1.296 times 6. 0.7776.
I like that answer. And now times 0.6 again. And how far do they want me to go here?
0.46656.
0.46656, so just a shade under half. Let me do that again because I didn't like that. And then one more time.
0.279936.
So about a quarter. So I'm going to do this in red with skinny marker. Skinny marker red. I'm going to connect these dots. I'm going to connect these dots. And it goes down like, oh, I don't like this. No, I got to go the other way. I got to hit it from this side because my shadow. Oh, God, that's awful. Let's try that again. Why is it so hard for me?
You need help, Cook?
I do. What do you think it's going to do after this? Is that thing ever going to cross 0? It doesn't make sense to cross 0, does it? What would it mean to cross 0? What would it mean in the terms of our word problem? Yeah, it's crushing through below the ground. Do balls do that when they bounce? No. It's just going to go forever and ever closer. It's going to get forever and ever closer to 0, but never actually touch 0. Okay? Last page. Does the exponential function 10 times 0.6 to the x power model the height of a bouncing ball? Does it? Yeah, I would say so. Yeah. And then, what does the function f of n equals 10 times 0.6 to the n look like for integers n greater than or equal to 0? Model. Now, let me go back to here. Let's go back to the graph. So, this is an important distinction. What does this point on the graph represent? The one I just made in red. What does that point represent? I'm sorry? What does that point represent? Remember, what are these numbers on the bottom? The number of what? The number of bounces, right? And then this, the y-axis, is the height after a bounce, right? So what does this point represent? Does it represent anything in this? It doesn't tell me what the height is between 0 and 1 bounces, does it? It doesn't say after a half a bounce, I'm at 7.5 feet. That doesn't even make sense, does it? So, this thing has limitations, right? This thing has limitations. Really, what I should have done is I should have left the red line out of it and just did the dots. That's what I should have done because that's the height after a bounce, right? And this is the number of bounces. Why did I draw this? Because we're going to do models where we see a gradual decline. Okay? We're going to have models like that. So I want you to see what the shape of it looks like. All right? Now, Jane works for a video game development company that pays her a starting salary of $100 a day. And each day she works, she earns $100 more than the day before. Ooh, I want that job. I want that job. But how much does she work on day 5? She works on day 5 and gets $500 just for day 5? Yeah. 500, yeah. $500 on day 5 alone. I want that job. If you were to graph the growth of her salary for the first 10 days she worked, what would the graph look like? Let me draw a little graph here. On day 1, on day 0, how much does she make? 0, right? So here it'd be 0. On day 1, how much does she make? 100. So on day 1, maybe there, right? On day 2, 200. So twice as far over, twice as high up, right? Day 3, so like that. Day 4. What does this look like to you? Yeah. Actually, I want to do blue.
Good color.
A linear line. Department of Redundancy Department, right? This is called... No, this isn't that. This is an arithmetic sequence. We also got another name. What'd you call it, Nick? Linear. They are synonymous. They are synonymous. Growth or decay? Growth. Thank you for your time, ladies and gentlemen.